So, doors or checkers? Doors. Doors or checkers first? Oh, you want the board too? Okay. So here's the thing. There's three answers I'm going to start writing down, but you won't be able to see it for a second here. There's three possible answers to the door problem. The first one is doesn't matter. The second one is switch. And the second one is don't switch. How many people think it doesn't matter? Anybody think it doesn't matter? One. I'm talking about what you believe right now. Pick an answer. This isn't American, like, let's not talk about it. We're just talking. Pick one right now. Pick one. Which one? Doesn't matter. 1, 2, 3, 4, 5, 6. It'll fix itself, and it won't fix itself. It's supposed to be like that. Okay. How many people think you definitely should switch? 1, 2, 3, 4, 5, 6, 7, 8. It's not bad. And how many think it doesn't matter?
No.
Oh, don't. Who thinks you don't switch? You should definitely stay the same. So you definitely think that you... Oh, maybe one? I know. I got to force them to do something. Well, here's the thing. If you have 3 doors, one of them is your prize door, 2 of them are empty. Okay? So let's play a really even more basic form of the game. You pick a door, and if it's the door that has the prize behind it, you get it. If it's not, you don't. No switching involved. So, first choice winner. What's the chance of guessing the first... yeah, can you hit the lights there? Yeah, choosing the proper door first is 1 out of... Yeah, it's 1 out of 3. First choice loser. 2 out of 3. Okay, so if we just play the game without any sort of modification, no switching, no nothing, 1 out of 3 of winning, 2 out of 3 of losing. So let's see what happens if you don't switch, these stay the same. Do you agree? If you don't switch, they stay the same. If you do switch, if your first choice is a winner and you do switch your answer, it automatically turns into always what? Okay, can you say it with more conviction than that? You always lose. There's only one place to win. So if you've originally chosen the winner and you switch, you automatically become a loser. Okay, what happens if your first choice is a losing one, or a loser, and you switch? If you switch, what happens? Say more specific. No choices. You always win. If your first choice is one of the empty doors and you switch, you will what?
Win.
Always win. Okay, so if your first choice is a winner and you switch, you lose, right? What's the chance that you pick the winner your first choice? So 1/3 of the time, if you always switch, you are going to always lose. If your first choice is a loser and you switch, you will what? Always win. What's the chance you always choose a loser? You choose a loser first. What does this mean? It means that if you always switch, 1/3 of the time you will lose, and 2/3 of the time you will win. So if you switch your vote, if you switch your guess, what happens to your chances of winning? Switch? No, what's the better way? Switch. If you switch, what did you say there? If you switch, you double your chances of winning.
And this is taking you take away a door.
Yes. Yes.
But here you just have to...
Shh. Game is played every single time. Don't out-logic yourself. If you originally picked the door that was the winning door and you switch, what happens? What is the probability that you will choose a winning door? 1 out of 3. If you choose a losing door to begin with and you switch, because we're always switching now, your answer will always, if you switch, you will always win. What are the chances you'll pick a door that is empty the first pick? 2 out of 3. So therefore, 1 out of 3 times you will, if you always switch, you will lose. 2 out of 3 times you will win. Pretty neat, huh?
I did totally
Hoping
outlogic
that you didn't.
So if you always switch, you will double the chances of yourself winning as compared to if you don't switch. Yes.
I agree with this. Can you explain why it's not just a 50-50 chance?
Because
now you know
I'm not explaining why ponies don't fly. I'm not explaining why. What I'm saying here is this: I could go on for 45 minutes and convince you that 7 is equal to 5. I could convince you that 2/3 plus 4/3 plus 5/3 is equal to 98. This is a sinkhole of logic. I carefully wall myself off around these fractions, because if we go any further, right now I have about, I would say about 13 or 14 out of the 16 people in this class firmly believing my explanation. If I try to explain it any differently, what happens is more people are like, wait a minute, but what happens if there's a bias somewhere in there? It isn't 50-50 because you have to look at it from the initial choice. Your initial choice is, it doesn't change anything. Initially, what's your chance of winning?
1/3.
What's your chance of losing? This choice, this added thing of opening a door and letting you choose again, doesn't change those original things at all. They are independent of one another. But if you do this thing, it changes that 1/3 chance of winning into losing, and it changes that 2/3 chance of losing into winning. Another way you can help yourself out a little bit is this. If you play a game that you're either going to win or lose, the chance of winning plus the chance of losing has to be what? 1, or 100%, right? So if you can concretely logic yourself into, I definitely think that if I switch my guess, I have 1/3 chance of losing, that absolutely means you have a 2/3 chance of winning. Do you understand it that way?
Oh, that makes more sense.
That's about as far as I want to go, because what's really fun about this one is that the more you think about it,
The less sense it makes.
Yeah.
the less sense it makes.
Because it feels like now you're taking a choice between, an empty door and a prize. Because it's just what it feels like. Then.
Yeah, because the way I did it experimentally.
Yeah, you're right. You're like, there's 2 doors, and one of them has a prize behind it, and one of them doesn't, right?
Right. I did
But
it.
that's different than the doors.
I did it with a marble under cups,
Yeah,
and so like.
yeah. You played the game.
Right, but then so I showed the door when I showed the door that was empty. I kind of like put it to the side.
Yep.
And then I think that just screwed with my mind. So it's like, oh, now it's 2 cups. It's underneath one of them, 1/2.
Yes.
So.
No, that's exactly what you're saying. Why isn't it just 50%? Why isn't it just 50%? Yeah. No, and I'll tell you this. There's still like 5 to 10% of me that firmly is still stuck over where you are, saying, shut up, logic. Like, I don't want to believe this. There's a lot of things like that. If there's a great XKCD comment. Here's how we're going to describe it. The original piece is going to have a value of 1. The value of the board is always going to be 1, because when I split this piece, what are the pieces going to be worth? Yeah, 1/2. And if I split any of those, what do they become? They become a 1/4, exactly. Now, no matter how I go about splitting these pieces, you have 1/8, 1/8. What is this one always going to be worth right there? If I placed a piece there, it's always going to be worth what? 1/8. What's this one always going to be worth? 1/8 as well. I'm just going to start filling all of these in. You can't actually do this in the game, but we're going to mark how much the space is worth if there was a piece in it. So we have 1, 1/2, 1/4. I just need you to see the diagonal bands. Do you see the diagonals? Okay, you see all these. Okay, so at any given moment, what's the value of the board always stays at what? 1. You cannot create value, you cannot destroy value. So let's look at the extreme case of this game. Let's say we filled in everything here. Everything. It's completely filled in. Let's just say there was a way. Let's just say we filled in all of the pieces outside. It's an infinitely big one. We're going to fill them all in. What's this one worth? What's this diagonal worth? 1/32. Yeah, so we have 1/32, 1/32, etc. And then this is going to be 1/64, and that's that diagonal, right? Do you agree with that? Okay, so I need to introduce one thing to you that you have not seen. I can't prove it because we haven't done limits. You do that in calculus. We'll see maybe a little bit of it at the end of this class, but not proofs. If I have 1, if I take the number 1, and I add 1/2, and then I add a 1/4, and I go on like this infinitely, if I keep on going forever, what does that sum to? It does sum to 2. You're correct. It does sum to 2. 1 plus 1/2 plus a 1/4. 1/2. I'm not proving it. Not proving it. What does that go to? 1. I just took away 1, right? So if I take away a 1/2 from both sides, what does this become? 1/2, right? No, not 1/12. 1/2. Exactly. Good. 1/8 plus 1/16 goes on. 1/4. it. I'm just telling. Yes. Yeah, go ahead.
Would you just get extremely close, not ever reaching it?
If you go on for infinity, you do. I'll give you another truth, and you can look this up for homework 2. Here's homework 2 if you want to look this. It's optional. 0.9999 repeating, that does equal 1. Look it up. There's many different ways to prove that. So if you can believe that, do you believe that yeah. I'm not going to prove these conclusively for you, but are you okay with that?
Yes.
Okay. So my question is, if I look at this first column right here, if I look at this first column, if I add all of those up, what do they add up to? 1/8. 1/16 plus 1/32, right? Well, how many of those columns do you see? I see the same thing right here. I see it here, and I see it here, and I also see it here. Do I see one more? Yeah, I do see one more right there. So what are those all equal? 1/8, 1/8, 1/8. Oh yeah, sorry. This is 1/8. What's the next one? 1/16. What's the next one going to be? 1/32, 1/64. Okay, keeps on going. That's nice. How many 8s do you see right there? I see 5 of them. What does this sum to? 1/16 plus 1/32? 1/8. I see an 8th. I see 5 8s. 5 8s plus 1/8 is what? Which is 3/4. We just filled up all of the rest of this space. All of it. What's the value of all the rest of the space? 3/4 is less than 1, which means what? Which means there must be at least 1/4, we're calling it value, inside the stairs.
Why can't you keep going out?
You do. We're going all of them. All of them. These all add up to 1/8. 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus the rest still equals 3/4. If you filled up all of the rest of the space, is there enough value out there? No. So where's the only other place the value can be? Inside the stairs. Inside the stairs.
How is it that you're allowed to just assign values and divide by divide by 2? Like why?
Well, hold on. You're asking why is this? Basically, you're asking why is that true? You're asking why.
No, I mean like why can you assign the 1 half, and the 1?
Okay, you're getting to the exact key of why I wanted to show you this question. First of all, I like the fact that you're not latching on to this. This right here, mathematical proof. You can look it up. You'll learn it shortly. Give it another year. You'll understand it completely. It's fine. The reason I'm showing you this question is the solution method. Is this an overly complicated solution method?
No.
Not really. Does that mean it's necessarily easy to find?
No.
Is there generally any correlation at all between the simplicity and the difficulty of finding it? In my experience, and what you'll notice is that sometimes the most brilliant, simple, clean solutions are what? The most difficult to find. I have a clear memory of another Hungarian professor with another great accent who was kind of like the most hyper person ever, but with a Hungarian accent. He would race around the room, and every now and then he would prove the same thing, but in a different way. And one of the things he said was he showed us this proof of there's a proof for there's an infinite number of prime numbers. There's hundreds of proofs for maybe not hundreds, but many proofs for that. And he showed us this great proof, something like that or something else. And it was this gorgeous proof. It's like 7 lines long, not very long. And we're like, wow, that's really neat. And he's like, yes, what they don't tell you is it took the man 5 years to find this proof. You're used to having problems that you solve in a certain way. You recognize something as a factoring problem. You recognize something as a rational function. You recognize something as a trig problem. And you have a certain toolbox for those problems, right?
Right.
Theoretically, how big can your toolbox be? It can be as random and as large as you want it to be. Until you notice this kind of pattern, are there other ways to logic this out? Probably. Is this a pretty clean way of doing it? Absolutely. I wanted you to see it because there are always different ways to do things.
Can you explain why the splitting up of it as a number with 1? Why does that prove that the problem is impossible?
Because of what I just said to you. I could have chosen any number I wanted to.
No, but my point is why is applying that value to each?
Ready? We're going to get back to what you asked before, which was this game. And I have not gone over this with the class, and I honestly haven't thought about it that much, although I have strong ideas. What happens if you had 4 doors?
Cool.
What happens if you had 4 doors?
The original
Just
method
Tom's
of winning.
multiplex.
The game is the same, okay? First of all, I have to clarify that. The game is the same. You pick a door, there's one prize. Yeah, but here's the thing. I'll clarify even further for this class because you asked about it. One opened door. So one of them has the prize behind it. You open one door. Now, from what you've seen already, what are you leaning towards? Do you think you should change your guess? Yeah, I think you should too. The question really is, though, how much of a gain in winning percentage do you get? That's the real question.
A little less.
I think it's going to be less. Oh, it's going to be less than double, absolutely, but prove it exactly. Not right now out loud. You can think about it tonight, but the point is, what happens in the generalized question? Okay, 4 doors. What about 5? What about 6? What about n doors?
There's going to be a pattern there.
Oh, yes, there definitely is, but just find it. It's different. It's an entirely different question when you introduce that 4th door. Entirely different question. Similar, but very different. You have to be very careful.